Hi, and welcome to Nothing is Rocket Science, a podcast where we talk about everything scientific and science related. Today we have with us Dr. Shiva Shakthi, who is she's a recent graduate in photonics from the Indian Institute of Science, Education and Research at Thiruvananthapuram in India. She works in the area of microwave photonics, which is an amalgamation of photonic principles and microwave engineering. Her research has focused on proving proof of concept experiments of microwave photonic notch filters and switches, which can be employed in radar, satellites, and electronic warfare systems. I will let her talk about it. I know these are big words, but she's here to talk about it and among other interesting things. Um, Besides this, she's also the co-founder of the No Nonsense Science Club, an initiative to debunk myths and misinformation in science. She is she recently completed a PhD and she just started a postdoc position at IIT Delhi. So welcome to the podcast, Shiva. It's great to have you.
Hey, Sandra, thank you so much for having me on this podcast. It's such a pleasure and to be here. And then I think I'm going to have a fantastic time talking about different aspects of science with you today. So, yeah, thank you so much for having me here. And then uh, let's see how it goes.
Yeah, sure. No, it's my pleasure. So, Shiva, like I got in touch with Shiva because of we follow each other on Twitter and we've discussed science a little bit, and we also have optics as a common background, and I really wanted to get her on the podcast and talk about something very interesting. And we were just having a lot of back. We were talking about what to discuss, and we had very heavy conversations for I think for almost about an hour about what to do, and then we eventually started talking about superheroes and like science fiction, and we were like, okay, we're both passionate and like we're both curious about this, and we both love superheroes. Why not just talk about superheroes and science fiction? And so we're like, oh yeah, then let's talk about it. And that's how this episode came to be. But before we get on to that, can you tell us a little bit about your research, your PhD research, and what are your findings and what are the applications of the outcomes?
Yeah, so as you said, I just recently graduated with a PhD from ICER, Thiruvananthapuram. So in ICER, I mostly worked in the area of microwave photonics, which is a combination of two different and very different areas. One is microwave engineering, and the other one is photonics. So this started around the 1960s as a field, and then what happened was before the area of microwave photonics emerged, there was something called, very familiar to all of us, we had something called electronics, right?
Mm,
And but there is a certain problem with electronics, using electronics for building devices which can be used in satellites, radar communication and all that. I'm not saying that electronics is not of use anymore, because we always need electronics, and any experiment that we are going to do will be fundamentally done on an electronic platform. And then once you get an idea, you extend it to the photonic platform or the microwave photonic platform, to be precise. So let me tell a bit about why electronic platform is not preferred. So the one thing is
mm,
that if you design a device using electronic components, it is going to be bulky in nature because of the mass of the different components that are used. And the second one is that they are prone to electromagnetic interference. So let's say that I'm working with a particular electronic signal or a microwave signal, and then it is always possible that if you are doing an experiment next to me using another electronic signal, sorry, another microwave signal, which is of slightly different frequency, there is always a chance that these two can, interfere with each other, which is not very good,
Mm-hmm.
right? So it's more like saying that, to give a better analogy, it's like, you have a crosstalk, which we don't need,
Right.
right? So one, it is bulky. Two, it is prone to electromagnetic interference. And the third thing is that it is going to be really huge if you make a system. For example, if you one is the mass, which is bulky, and the second thing is and the other thing is that it is going to be huge, and you don't want anything to be huge, you want it to be as small as possible, right?
Right.
As Feynman said, you're always, there is a plenty of room at the bottom, so you're just, you
Mm-hmm.
want to head towards smaller and smaller things.
Right.
So
Right.
we had milli, and then you had micro, and now we are at the nano stage. So you
Nano.
want everything to be as small as possible, and
Mm-hmm.
maybe we'll go beyond that. It is quite possible that we'll go beyond that as well. So that's where photonics comes into play, because let's say I have a sensor which detects the signals, and if that is going to be made of electronics, it is going to be at least the size of my hand, okay, my palms.
Mm.
But if the same thing, if I'm going to design a sensor using photonic principles, it's just going to be a size of the tip of my finger. So
Mm.
that's a lot, right? The ratio is going to be huge. So this is one reason why we jump into photonic principles and microwave engineering. And this is pretty much what I do. So this is basically the fundamental of why I chose microwave photonics over electronics for my experiments. And so why microwave photonics? So what is microwave photonics? As I said, is an amalgamation of two things: the
Mm-hmm.
microwave engineering part and the photonic principles part. So I use these principles for designing devices like notch filters and microwave photonic switches and so on. So these are components which are used in places like satellites and
Mm-hmm.
radars and telecommunication sector and all that. For example, I have two signals. Let's say I have one signal, sorry, and I want to switch them between two different houses.
Okay.
So as the name suggests, I use what is called as a switch, right? So
Mm-hmm.
when one gets turned on, the signal goes towards the other house. And when that gets turned off, the signal goes towards the next house,
Right.
right? So this is one place where where a switch gets used, and then, for example, notch filters. So usually in radar environment, you have a lot of signals, a lot of microwave signals which are coming, and then you want to detect. You want to have that one frequency that you want to work with. So what you
Mm-hmm.
do is basically suppress all the other frequencies which come. So these are called as interferers, because it's basically interfering with the signal that you need. So you put what are called as notch filters, which is going to suppress all the other frequencies, and it will just let the desired frequency to come, which you
Mm-hmm.
can then work with. So higher the suppression, better the rate at which, or better the accuracy with which you can do the experiment. So
Mm-hmm.
that's pretty much what I have worked on. So this I'll be extending at IIT Delhi as well. I'll be working on similar projects at IIT Delhi. The difference will be that in IISER Thiruvananthapuram, I mostly worked using optical fibers.
Mm-hmm.
So those are the simplest platforms to work on the to do the different experiments, especially photonic experiments. But fibers, again, I use like 2 kilometers of fiber, which is going to be, which you might ask that, okay, fine, 2 kilometers of fiber, that is still bulky and then huge. And
Right.
then and the entire experiment runs on a table which is about 2 meters, 2 meter into 1 meter. So again, you can say that this is going to be very bulky. As you said, I work on proof of concept experiments. So, my
Mm-hmm.
idea is to give, acha, this will work, right? And
Right.
then, so now what we're going to do is that once this is done and once I know that the proof of concept is working, what we're
Right.
going to do is integrate the entire thing on a chip, which again, as I said, is going to
Mm.
be the tip of the finger, right? So
Right.
this
Right.
entire 2x1 table and the 2 kilometer fiber, everything is just going to come onto a chip, right?
Mm.
So 2 kilometer of fiber, how do I change it? Is that when you pass light through 2 kilometers of fibers, it produces certain level of non-linearity.
Mm.
So nonlinearity is a highly intense process. Like we in school, we must have briefly studied about Raman scattering. So Raman scattering is the
Right.
reason why the sky is blue.
Blue.
So
Mm-hmm.
similarly, there is another type of scattering called as the Brillouin scattering, which is
Mm-hmm.
very similar to Raman scattering, except that the reason is slightly different. So longer the length of the fiber, stronger is this Brillouin scattering.
Mm-hmm.
Okay. So instead of using longer lengths of fiber, if I use a very small chip which is going to have a higher nonlinearity, I can produce the same effect on a chip which is of micrometer length.
Length.
Okay,
Right.
so either I need to use a medium which is longer in length with a low nonlinearity so that at the end I get a high nonlinearity as the light passes through the medium, or I use a material which has a very high nonlinearity so that I don't have to use something which is very long, and then I can produce the effect using a very small chip. So, yeah, so that's pretty much about what I do. And
So
yes,
where
so
do you
that's what I do.
see, yeah, where do you see these apply in real life? Like where can
So
I
as
see
I
them?
said, yeah, so as I said, these will be used in areas like defense and
Mm-hmm.
electronic warfare and
Okay.
all that. So radar is a primary component of electronic warfare. Right.
Okay.
For example, you have a lot of signals which are coming, and then, for example, you have an enemy plane, and then you have your home battleground. And what happens is that the enemy plane basically sends the signals, the microwave signals,
Mm-hmm.
and the microwave signals might fall on one of the receptors which is present in the home battleground, and if it reflects back, it is going to the enemy ship, oh sorry, the enemy plane is basically going to know that there is a certain target in this area and they might attack it. So
Right.
right, so before that, if you use these components like switches, notch filters, not separately but a combination of this to create a device,
Mm-hmm.
what you can do is basically jam the signals, right?
Right.
So when you
Mm.
jam the signals, it is not going to get reflected back at all.
Mm.
So that is like, you basically distract your enemy. So that's
Okay.
one place where you design it, where you use it, and these still
Mm.
things are yet to be made more accurate and all that. So they are still being proof of concept experiments. They have been extended on chip, but maybe sooner we'll have devices which are just chip scale, and then
Mm.
more accurate jamming and all that. So that's about
That's no, that's really interesting, especially, when the application is in warfare and in radars. It sounds really, really interesting. Um, yeah, speaking of light beam and lasers, I thought this is a good time to jump into our topic for today, that is the science behind superheroes and science fiction science fiction objects that we see in movies, whether they can be recreated, and if recreated, are they functional? So, speaking about lights and light beams and probably introducing lasers, um, I thought we should talk about our first X-Men superhero. the first X-Men, that's Cyclops. For those of us who know Cyclops, he absorbs the energy and then he shoots it as laser called optic blast from his eyes, which which he has very little control of. And the optic blast is so powerful that he can like destroy buildings or mountains. And so because he cannot control it naturally, he wears something called he wears visors, and these
Yes.
visors are made up of ruby quartz. That's the material. So, yeah, can you tell us a little bit about this and, how does that work? And, does ruby quartz really have this ability to control the amount of, the optic blast, the intensity of the optic blast that's coming through his eyes?
Yeah, so first of all, yay to X-Men.
Yep.
So, a favorite series. And so, coming to Cyclops, the entire energy that he draws from the environment, and then,
Hmm.
as you said, he has this
Converts it,
ruby
yeah.
quartz where it kind of gets amplified, and then this
Hmm.
amplified energy is then thrown out, right? Which
Right.
basically destroys the environment and any surrounding objects. So the central theme here is with the ruby quartz,
Hmm.
right? So ruby quartz is actually a material which is used in lasers, especially these are lasers which are called as visible lasers. Like you have different types of lasers
Hmm.
which extend over different ranges. So these are called visible lasers because it's ruby quartz laser basically emits light which is red in color, and
Hmm.
then you also have lasers which emit invisible beams of light, which is
Hmm.
another fantastic area of research. In fact, I for my experience, for my experiments, I use invisible light or invisible
Hmm.
beams of light, and these basically lie in the mid-infrared region. Though it is called as
Right.
the mid-infrared region, they are not red anymore. They are
Hmm.
basically invisible. And fun fact, these are the basically the light or the telecommunication, you call them the telecommunication wavelength, right? So that your
Okay.
entire internet, the bandwidth of the internet, and why you're able to talk and why we are talking right now is
Hmm.
all because of this invisible radiation which is passing through the fibers, which is at the bottom of the sea,
Right.
ocean bed. So coming back to ruby quartz was the first material which was used to generate or to design the very first laser. It
Hmm.
was the work was carried out by this wonderful scientist called Charles Towns in the MIT laboratory back in 1960s.
Hmm.
So why ruby quartz is because it is, as I said, it's a medium where if you give a very small amount of power, it can get amplified a lot. So in laser, every laser has two components, two major components. There are also other components. One, you
Hmm.
have reflective mirrors. And in between these reflective mirrors, you keep your gain medium. So it can be anything. It can be a gas, it can be a liquid, or it can be a solid crystal. So in this case, it is basically a solid crystals, which is a ruby quartz crystal, right?
Hmm.
And then you apply a very small amount of light to it, and this light interacts with ruby crystal. And then when you just allow the light to pass through the ruby crystal, you're not going to get such an amplified radiation. Okay. But
Right.
however, if this light keeps passing back and forth through the ruby crystal, what happens is over a period of time, the intensity of the light keeps building up.
Hmm.
Okay. And then it comes out where it is much more amplified. And
Hmm.
why do we need a laser? Instead, you can always have red lights, right? I mean, for
Hmm.
example, you can have a torch light, which will be red in color. But why Cyclops uses this ruby quartz laser, or why the concept of laser in the first place, is because there is something called as the concept is called as coherence. So
The
if
concept
you
is called what?
shine a
Sorry?
torch,
Oh, coherence. Yeah, yeah.
coherence.
Right,
Okay. So if you shine a beam of light from a torch, what happens is that you will be able to see you're in a dark room and you shine a torch, you'll be able to see that the light disperses.
right,
Okay, so the torch might be very small, the diameter of the torch is very small, but if you're shining it onto a wall, you will see that the diameter of the light beam which is falling on the wall is very much high, which is it's
right,
much larger
right,
because of the dispersion. However, let's say you have a laser and the opening of the laser light, or the opening of the laser itself is like 1 centimeter of something. So that you shine on the wall, it is again going to be 1 centimeter on the wall.
right,
So the intensity gets focused exactly on the wall. So if you
right,
shine a light which has a certain intensity, the intensity is going to be same when I shine it on the wall. However, if I shine an intensity, if I shine a light from a torch onto a wall, what happens is that the intensity decreases a lot.
right.
It decreases by 4 times of what it initially was.
Mm-hmm.
So if you want to connect it with how Cyclops does it, is that again ruby quartz which he has is like the gain medium, and how he uses the environment to gain all the energy can be thought of as the initial pumping which happens. As I said, you have to initially pump the ruby quartz crystal, so it can be thought like that. And then we also said we you also said that sometimes it just goes out of control. And
Right,
in laser, you always have a turning off mechanism. You can
mm-hmm.
always turn off the laser and then it just goes stop, and then the light is not going to pass through anymore. But in case of like Cyclops, I think that's going to be a bit of science fiction over there, that like he is not in control of that.
Mm-hmm.
So it's like two people working, and one person has control of one person has the switch and the other person cannot control it. So you
Right.
can think of it that way. So I think you have a bit of science and a bit of science fiction over here,
Mm.
which
Yeah.
have combined to have what is called as visor, or we have Cyclops there. But nevertheless, an interesting topic to, especially if you want to talk to kids about it, I think it's a great start to tell them about Cyclops and ruby quartz, especially because the name is just the same. It's ruby quartz, it's ruby quartz otherwise as well. So it's just a
Yeah.
fantastic place to start the whole thing. So
So here, so here he's using ruby quartz to control the intensity, right? And not amplify it. Not, yeah.
to
Okay.
generate the light, yeah.
To generate light. No,
To
but
generate
he.
as in to generate the first beam of your laser. So your ruby quartz is actually the gain medium. So
Mhm.
an initial intensity actually falls on it, and then it keeps reflecting back and forth through the
Inside
ruby
the
crystal,
crystal.
which is gain medium. Yeah, and then it
Mm.
gets amplified. So yeah, you're right. It's the gain medium.
So, uh, then why is it used as protection? Because the optic blast that comes from his eyes are uncontrollable, right? Like, I mean, I understand there is that fictional component here, but what is the purpose of wearing the visor if it's not helping him control, or I mean, if it's amplifying it, then it's not useful there, is it?
I would say that that's again a bit of science fiction over there, because
Okay.
at the end of the day, you don't want to damage your own eyes, right? So,
Mm-hmm.
light, especially if you shine on other objects, there is a high chance that it is going to get reflected back. at you, especially
Mm.
at certain angles, right?
Mm-hmm.
So
Right.
it's so the idea is the same, and then you want to build up around that concept, and then
Okay.
you have the visor over there. So that's pretty
Well,
much
like,
why
like you rightly pointed out, there's some parts fact, some parts fiction. And I
fiction.
guess, yeah,
I
I
think our
think we
whole
should,
talk is going to be about some parts science and some parts
some parts,
fiction. So
right,
yeah.
right. Um, well, moving on from the Marvel universe to, a galaxy far, far away, uh, lightsabers. So, can we? I know there's been a lot of talk about recreating lightsabers, and like that we've had, I've seen lightsabers in Comic Cons or in other like comic book stores, but can we actually recreate? Can we create a functional lightsaber, and will they be as strong and then cut through any material? Like, can we have something like that? Is it possible to have a functional lightsaber as we've seen in the Star Wars
The answer
movies?
is again both a yes and a no for a
Okay.
lightsaber. Because a lightsaber, as I said, the principle is same. It's basically you have a laser light
Hmm.
with which you're going to have such a high intensity, and with such a high intensity you can always have a fight, and then you can destroy people and all that. Well,
Hmm.
disclaimer, don't do that.
Of course,
But
yes.
so the idea is that you but the idea here is that you cannot contain the light over here. Okay, so laser light is that if you shine a laser light, it's just going to extend as much as possible. So
Right.
you can have a lightsaber. Typically, what we see in Star Wars is less than a meter, right? And then they hold it, and then the light extends for about a meter or so,
Hmm. Hmm.
right? But if it is a laser, you cannot really control the light, and that's one aspect about lightsaber which people are working with a lot. What you
Hmm.
can do is so it's basically a clash between two different mechanisms. So the lightsaber that we see in Star Wars is something which is very coherent. If you see that there is no dispersion, like there is light coming out of your lightsaber, but it is not a conical thing, it's exactly a straight thing,
Right.
right? So whenever you have something which is very straight and then there is absolutely no dispersion, it is called as coherence,
Right.
as we discussed previously.
Hmm.
However, so we have coherence part which gives you that lightsaber thingy, that the light coming out of the lightsaber is like straight and intense. But on the other hand, we have something. So the intensity will stop only when there is huge dispersion. So on the other hand, you have dispersion. Dispersion is
Right.
that the light comes off the lightsaber. It's more like having a torch,
Right.
right? So if you have a torch and you turn on the torch, the light is going to come out of it, but after a certain point in time, it's just going to disperse and you're not
Right.
going to see anything,
Mm.
right?
Right.
So it is basically a clash between these two things. So maybe if there comes a point where we'll be able to tackle the coherence and also control the coherence after a certain length. As of now, we have no control over the coherence length of a
Hmm.
laser. So we call it the coherence length. And
Right.
coherence length is always of the order of few kilometers and tens
Mm.
and hundreds of meters. But if at some point we'll be able to get a coherent source whose coherence length can be just 1 meter or something, then yes, we can have a lightsaber.
Hmm.
Yeah.
And it'll be strong enough, and will it be strong enough to cut through materials and
Yes, yes,
other strong
definitely.
things?
Yeah.
Okay.
But for
Well,
now,
I
I think a lot of toys are coming up where they use this contained tube and then they have
right.
a red and a blue light. So that's not that can be you can say that that's a lightsaber, but that's not lightsaber, right? Like you have to turn off and turn on, and then it
Right,
just completely vanishes. There is no material after that. So yeah,
right. So
that's
for
the
the
thing.
for it to function as a lightsaber, you would need lasers, which has that reduced coherence and that lasts only for a short distance. Okay. And
Yeah, yeah.
I know for a fact that there's some ongoing research about about this. But did they ever come up with a material like anything in the recent past?
In the recent past, you mean for the lightsabers, right?
Like the coherence that you
So
were talking about,
not
like
exactly.
hmm,
Coherence is true for any laser, if you ask
right,
me. If I do, like they are coming up with, so they are not exactly making materials for lightsabers, but they are making a lot of materials
right.
for other applications, right? So. Um, Nothing that I can think of at the moment which can be exactly used for creating a lightsaber, but
Mm,
yes, there are blue lasers which emit blue light, and then there are
mm,
lasers, as we know, in the case of ruby quartz crystal, which emits a red light.
red
So you
light.
can say that you have a small laser light, you get it for a couple of bucks, and then you shine a red laser. It's that it's a basically a toy these days, except that you're
Right.
not supposed to shine it right
Shine it
into
away.
your eyes. But it has come up in the market, and it's quite famous, and then it's making rounds in the market. I mean, I think I used one when I was a kid, so that's like back
Mm,
15 years, for 15 years. So now you might have extended version of that. So
right.
I went for a comic con in Hong Kong, so 3 years before, and then they had something like that, and I
Mm,
purchased one of that because it brings in a lot of nostalgia. So you
right.
can actually think of this red ruby quartz laser to be a lightsaber which is very long. So
Mm.
yeah,
So
so
you would
maybe
probably
you yeah, so maybe you have a lightsaber, but then it's huge. It's
it's
very
long. It's
long,
too long.
and then
Right.
it's long, yeah. And I think that's okay, right? If you have something which is very long, and you'll be able to destroy or damage anything which is going to be at a very long distance, then why not
Maybe.
have it?
Yeah. Yeah. So
Yeah,
it is functionally possible to recreate or like to have like a functional
yeah,
lightsaber.
that's what I will say. Except that you have
Hmm.
to, if you wanted something small, as in the movie, to such that it looks like a sword, right?
Like a sword. Yeah.
Then you might have to control the coherence length a little bit.
Mm, mm,
And otherwise, yes, why not a longer
yeah.
lightsaber? I mean,
Yeah.
because I mean, it's okay, right? And in fact, it's much smaller, right? You can just hold it in your palms, and then you just turn it on, and then you get a very long lightsaber. Why not?
Maybe. Yeah.
Except
Why
that you
not?
have to increase the intensity by several folds. But
Mm.
yeah, we are talking about science fiction, so why not? The
So why
question
not?
is
Yeah. Why
always
not?
why not? Yeah.
Yeah. Or like your research is just a proof of concept that yes, this is
It's
possible.
a proof of concept.
Yeah.
Absolutely. Yeah.
Yeah. Yeah. And
Yeah,
no
we do.
longer science fiction.
Oh, yeah. Absolutely.
Yeah. And then now quickly moving on to Flash, pun intended. Um, is it true that he can at times run at the speed of light? And is that even possible?
As of now, every time you talk about a material or light, you talk about two different aspects of light. One is something called as the phase velocity, and the other one is called the group velocity. Okay, let's not talk about these terms. So
Mm-hmm.
phase velocity is basically how someone would pass through vacuum. What would be the speed of someone passing through vacuum? Because in vacuum you don't
Vacuum.
have any kind of resistance,
Right.
right?
Mm-hmm.
And in whereas if you're passing through another material, if it is light passing through another material, you always have resistance from the material.
Mm-hmm.
So it can either, if the it's all about the refractive index. If the
In,
refractive index is going to be very high, like let's say, okay, not even refractive index, like let's say the opacity of the material is going to be very high, then when you shine the light, it's going to be, the time it takes to come out on the other side is going to be very, very less,
right.
right? And in the case of flash, let's assume that the whole concept is running around, is happening in vacuum. So if
Mm.
it is going to be happening in vacuum, and if we assume flash to be light, uh, yes, he can pass through at the speed of light. Yeah, because he is light in himself, right? You're just giving him an image of, which is called flash. So, as the
Mm-hmm.
name says, it's flash, it's a beam of light. And
Right.
if you consider the entire scene to be happening in vacuum, then he can definitely pass at the speed of light.
But he's on Earth. He's actually not in vacuum. So so is it like I was reading about this a little bit. So it's like he cannot be faster than light all times, but there are times where he can be.
He can,
Uh,
yeah.
So is that
Let's say
is
let's say you are in a room where there is vacuum,
Mhm.
and see, these are superhuman people, right?
Right.
So they can survive in different environments.
That's true.
So yeah, so if that room is going to be made up of vacuum, then yeah, especially then in those scenarios, he should be able to travel at the speed of light, and
Hmm.
I don't see problem, except that he has a huge mass. And if you consider mass as a concept, so there is nowhere a mention about his mass or anything,
Hmm.
right? So if he is just if you assume flash to be like just a very, very small particle, then
Entity. Yeah.
he can, yeah,
Hmm.
it's
So he
about
should
expanding between speeds, yeah.
so he should like not only be fast, he should also be tiny to
Yes,
actually
yes,
travel at
yeah,
that light.
yes, yeah.
Hmm.
And so basically in science, as I said, you have something called as the group velocity and the phase velocity. Phase
Mm-hmm.
velocity is always what is the speed of light in vacuum. And
Right.
that is one, that is like a reference frame. And group
Right.
velocity is how light passes through different medium.
Mm-hmm.
Okay. So that is the comparative thing. So in case of flash, your group velocity is equal to your phase velocity. So he might pass through a fictional medium, but in that fictional medium, your phase velocity is equal to your group velocity.
Mm.
So that's what is happening. So again, that's a fictional medium. So that fictional medium here is a fictional earth. So,
Yeah, it could be anything. Yeah. Where he maybe his mass is almost negligent, which is why he's
negligent.
able to. Hmm. Okay, that's yeah, that's pretty interesting. Um, we're talking about the whole concept of time and like speed and stuff. Um, I'm gonna ask a very cliched question. Is time travel possible? And why is that time slows down, when you're traveling at certain speed? And I was also reading, I read somewhere that you can go to your future, you can travel to the future, but you cannot travel to your past. And there are certain experiments that people have conducted. So yeah, like, interstellar, if that's actually possible.
So for as of now, it has mostly remained a theoretical concept.
Mm-hmm.
And people have done experiments. It's basically not exactly time travel experiments, but rather other experiments with which you can define time travel. And
Mm-hmm.
I'm just going to leave this thing open to ponder over it a little bit
Yeah,
for
sure,
others who
sure.
are listening to the podcast, because an excellent place to start thinking about time travel would be the movie called Interstellar.
Mm-hmm.
Um, Fantastic movie. And then it's a bit tricky as to explain time travel, and why it is going to be possible to travel into the future. So somewhere intuition says that you won't be able to go to the past and change your past such that it reflects on the future.
Right.
So for me myself, it took a long time to understand. I think I still don't understand time travel. And then, if I'm going to start talking about time travel, I'll be going blah blah, and then we might end up somewhere else.
Mm-hmm.
So I think I'll just leave it open, but then we can discuss it, you know, if you wish to.
Yeah,
But
sure. If
then
you,
this is something uh, which I'm not very uh, I won't say I'm not very convenient with. It's something where something which I myself don't understand in a very
mm,
great detail. So
okay.
better not to, you know, give out the wrong facts.
Sure.
Though
Right,
it is
right.
in the science fictional world, I think it has been described in a beautiful way. And
Mm-hmm.
then even my explanation would be coming entirely from science fiction and not science. And so I'm just going to leave it to movies and other podcasts where people would explain it much better. So
Okay. And if you have to give us some details about how it is possible in a science fiction world, or what is the science behind, okay, to call it science behind science fiction. So if you have to just explain it from a movie concept, like how we discussed Flash or like the Cyclops, this, some parts facts, some parts fiction. If you can give us some details about that, that also would be great. Like, it like you said, you can leave it open-ended to our interpretation, and our readers can go and further read about that to know if it's possible or not in real life.
So yes, so you can have different movies. You can have science fiction concepts based on it. So over there, the idea is that it's all about speed again. How you'll
Hmm.
be able to travel to the past or towards the future. You draw what is. It all depends on what is called as a world line. So I'll give a simple example of how you can imagine time travel to be.
Hmm.
So you might have, if I generally ask a kid what is the, a path of every planet in our solar system, the kid would say that it is an ellipse, right?
Hmm.
So we have always seen it as a ellipse. But if you look at it from a time travel perspective, it is no more an ellipse. It's rather an helix. So time travel is
It's a
basically
helix.
it's a
It's a
helix. Yeah.
helix. Okay.
Yeah, it's no more an ellipse because you won't be studying. It's no more just spatial in nature. Time travel is rather a mix up of both space and time. So, if you read a
Hmm.
little bit about Einstein's relativity concept and everything, so you will see that everything is a mixture of space and time.
Hmm.
So it might be ellipse at one level. If you see that it might be an ellipse, but slowly it's also evolving in time. So it is like you're
Hmm.
stacking up ellipse after ellipse, and these ellipses are all connected because these are not, time is continuous, right?
Right.
You're not stopping time anywhere.
Hmm.
And when you don't so you have a stack of ellipses and you want to connect these ellipses, then what it happens is basically a helix, right?
Mm,
So you have, let's say you have three ellipses and then you want to connect these three ellipses, then basically the first two ellipses you will connect using a string or something, and the second and the third one you will connect with a string or something. So that's pretty much how you can easily see time travel. So that's a fundamental place where time travel or the explanation of time travel comes from. So uh, it's basically a space-time
continuum.
yeah, space-time continuum, and then
Mm,
all the light and the speed of light comes in. So again, I'm not an expert with this.
yeah. No, but I think a lot of these superhero movies, like even in the Avengers, I guess they were talking about the space-time continuum. So this concept is kind of widely spoken about, especially in the science fiction genre. And I guess there is a lot to go back and figure out ourselves as to what is possible and what is not. Um, so yeah, so I think that's great that this is kind of probably what happens there, but uh, like you said, yes, not all of us are familiar with it, and it's always good to do our own research to understand if this is possible or not. Um, and I thought I'll save the most save the best for the last. Um, would it be possible to recreate a functional cloak of invisibility as we see in the Harry
Oh
Potter
yeah, totally. Yes.
movies? You
Yes.
can't you can't like you can't talk about all this and leave Harry Potter out of it. I know it's not science fiction, I know it's not science, but why not? We need a bit of magic in our lives. So yeah, the cloak
Yeah,
of invisibility.
that is something people are working on, with full power and excitement and everything
Hmm.
else, because Harry Potter is something that, even the very small kids are like, so the very first concept where people go, the kids go wow, or even the adults for that matter
Yeah.
go wow, is about the invisibility cloak. The very first thing, right? So invisibility cloak is something that people are working on. Again, it depends a lot about light. So let's say I have an object which is present, two objects which are present, and then what happens is that if the object has a lot of gravity and there is light coming from behind the object, what can happen is that, simply saying, the light will be completely absorbed by this object when the gravity is very, very high. Something similar to
Mm.
black holes.
Right,
So
right,
right, so you cannot see anything which is the, you won't be able to see something, so basically light bends around this object and comes, so
right,
you will only see what is there behind this object, but you wouldn't be able to see anything which is there exactly in front of you.
right.
Okay, so this is a phenomenon which was again described by Einstein when he was around, and then this is called as gravitational lensing. This is a
Mm.
very important concept even in astronomy.
Mm.
So that is one place where invisibility comes in, but it is not exactly invisibility cloaking, but it served as a primer for invisibility, creating invisibility, exploring invisibility, and all that. Okay,
Mm.
so why did it come into places? Because let's say you are observing the spectra of stars, and what happened was, when they took you basically use spectrometry to observe the spectra of different stars, and they
Mm.
showed the spectrum of two different stars, but rather when you were imaging, they were able to see just one star.
Mm.
Okay. So it's basically the light from the other star is completely blank. You're not able to see that.
Mm.
So this is where the primary idea of lensing came into picture as to why you're not able to see something. And so it's basically, so maybe there are so many stars which we haven't explored, we don't know about it, except for the gravity part and all that. So that is the primer for lensing in the bigger picture. On the smaller picture, if you really want to create a cloak or something, there is something called as metamaterials, where all your light and the properties of light, everything changes. For
Hmm.
example, if you have the process of what do I say? If you have the process of refraction, you know that the light falls on a certain medium, and
And
then
then
the
bends.
angle becomes less after refraction. But however, if you have a metamaterial, you will see that the angle becomes greater and greater. It becomes larger and larger. So
Hmm.
everything kind of gets reversed in the case of metamaterial. So this is one fundamental material which has been explored a lot in order to
Hmm.
create, you know, invisibility cloak. And they
Hmm.
have actually created an invisibility cloak in several labs around the world. And this I think even in India people are working on invisibility cloak, as far as my knowledge
Hmm.
uh, concerned. And then, but on a theoretical scale, not at an
No, no.
experimental scale as of now.
Hmm.
But it's a very interesting concept altogether. So metamaterials, it's basically a combination of what are called as electronic small electronic structures which will be modifying the light which falls on them. So
Hmm.
it's the whole concept of invisibility is about modifying light which falls on it. You
Hmm.
change the way reflection happens from each of this
Right.
component, right? You
Right.
know that there is a component. For example, you have a ball and you have a wall in front of that, and
Right.
then light falls on that particular wall from a different direction. If you're standing such that you're not able to see the wall and you will be able to see the reflection, that
Hmm.
happens only when light falls in a certain direction
Right.
and the reflection happens. But rather, if instead of the light reflecting ball, the light reflects off the ball in the direction in which you're standing, but rather it reflects in a direction completely different from your eyesight, then you will almost say that there is no ball in that place.
Right. Hmm.
Right, so that is the concept of behind creating invisibility cloak. But for now it's no more, it's not a cloak, it doesn't have a flexibility and all that. It
Hmm.
is rather a plain sheet
Like a
which is
sheet.
very
Yeah.
rigid. Yeah. Right. But
When
yeah,
no,
go
when you
ahead.
were telling me, yeah, when you were telling me about this, I was reminded of, in the Avengers, I think in the first Avenger movie, they, they show when they assemble all the Avengers on that submarine, ship kind of a thing, and then that becomes an airplane, and then it vanishes in the sky because, they turn on the reflectors, and then all of a sudden the airplane is there, but
Yeah,
nobody can see it. Is it similar
yes.
to that? Is it similar to what
Similar to
what this
that,
is
yeah,
reflecting?
exactly.
Mm.
I think that's a very good example of how you can think of invisibility and
Mm.
all that. So you basically turn the direction of the reflectors.
Right.
But then you do it manually. Here, because of the principles, the way the reflection happens itself changes. So as a person,
Mm.
intuitively it cannot happen in that direction, but you tweak the material such that the reflection happens in the opposite direction. So for
Mm.
someone standing in front, you won't be able to see that.
Mm. And have you heard of this? It's called super black. There's this color called super black. It is so black that I think it absorbs about 99.7% of the light. So
Yes.
like I think there are a couple there's a species of a bird which is of that color. and it is so black that it is almost like invisible. So maybe, instead of using electronic chips or something, they could also use a material with this paint, um, and which absorbs all the light, so you don't get to see someone behind. I don't know. I'm just throwing
Yeah.
ideas.
Yeah, super black is again an interesting topic. Super black is something which I got introduced to a greater detail very recently. There's this channel on Facebook. I don't know if it is available on YouTube as well. So there is this channel called the Action Lab, and he does very beautiful experiments. I think that is something everybody has to check out. It's
Mm-hmm.
called the Action Lab, and he does a lot of experiments on how, even there is an experiment on how well, you have a capillary which is running for about 20 meters or so. He has that dipped into a fluid, and then the capillary is running all the way up to the top of a very of a skyscraper, not exactly a skyscraper, up to like 7 to 8 floors, and you will be able to see that the water rises, and then at a point it won't be able to rise because there is gravity. There is a lot of gravity, and then there is, this countering force between gravity and then capillary action. Capillary action always
Action.
happens in the upward direction, and then there is gravity which is pulling in the
Gravity.
downward
Mm-hmm.
direction. So because of that, there is a little bit of boiling which happens. So you will be able
Mm-hmm.
to see that it starts boiling at that point. So
Mm-hmm.
that's an interesting thing. And
So
yeah, so
he
as you say, I think that's a very good proposal for a science project. We can use
super
black.
black, and then
Yeah.
okay, yeah,
But except
like
that in
probably
super black, you will be able to see that there is something which is black. Except that, as we said, there is something present. You won't be able to see what is present behind it
behind
because
it,
it's going to hide the entire thing
right?
along the line of sight,
Yeah,
right?
but I think you
But
would
in the case
probably
of,
see something black, right? You probably will see something black,
yeah,
but not something invisible. It's
yeah,
not going to be completely
exactly,
invisible. Yeah, you're
invisible.
right.
Yeah,
Yeah.
you won't be
Hmm.
able to see, like, even in the case of Harry Potter, you will be able to see what is there behind the person. If
Right.
Hermione is covering her, or Ron is covering himself, Harry is covering himself with an invisibility cloak, you'll be
Yeah.
always able to see what is present
Behind it.
behind it. But in case of super black, you will see that there is a structure in front of it.
Right.
So,
Right. Hmm.
right along the line of sight, it will just it won't bend light. So that's what I mean.
But
Ella,
that got me thinking, if say for example, not the super black, but the concept of the metamaterials that we were talking about, you said that you can see the objects which are behind the person, but you don't get to see the person in the cloak, but people behind the person. uh, how is that happening? Like, you need the light to pass through something to see that. So how is that the light is not so do you mean to say that the
basically
light is
what happens
selectively
is,
blocking? Is it
yeah, the light
selectively
is
blocking?
selectively blocked. Yes.
Hmm.
So you have a ball, and there is light coming from behind the ball. So light is what carries information about what we see,
Right.
right? So in case of invisibility, so you have something which is present, a ball is present, and you cover the ball with this invisibility cloak, and light,
Hmm.
what happens is light bends around it and comes.
Hmm.
Okay, the light
Okay.
comes, it bends around it, and then it comes in the front. So whatever is
Ah,
there in the center, you won't be able to see it.
okay.
So
Okay. Hmm. That's interesting. Yeah, that's really interesting. Um, so yeah, this was really, really interesting. I'm sure we have a lot more questions, but I don't want to inundate everything in one podcast. We could probably come back and answer some more questions on science fiction or superheroes. But before we leave, you are actively um practicing science communication, and that is something that I am passionate about, which is why this podcast came into existence. So I asked this question to all the guests, to at least like the guests who are science communicators. So, what, according to you, is science communication? What is your personal definition of science communication, and why do you
For
do it?
me, science communication is more about taking science that you do, because I think everybody has a responsibility to know about science,
Right.
right? Because the science you do is funded by the public
Hmm.
for most of us.
Right.
So even apart from people who do science actively, it is also important that people who don't do science need to know about it, right?
Hmm.
So that's what is science communication. So you have to take the science that you do and deliver it to the people.
Hmm.
That could be kids, that could be elders, that could be people who don't, who have certain kind of a disability, and whatever it is. So in
Right.
whatever way possible, take the science, take it as a responsible science communication. According to me, more than delivering something to people, it's about a responsibility. It's your responsibility that, it's like how voting is a responsibility. I think in a similar way, science communication is a responsibility. It's a responsibility of anyone interested in science, or anyone doing science. And because everything I we do these days, especially from high end institutions, are all publicly funded. So it should be
Right.
a responsibility. I think it should be made much more active. Maybe it should be mandatory for people. I think
Hmm.
it's a big word, but I think it should be made mandatory for people to communicate science in whatever way
Hmm.
possible. Not
Right.
exactly go give talks and all that, but whichever way possible, you can do it. So,
That's a very interesting perspective, which is exactly why, because we don't have a hard and fast definition for this, and I've had about 4 or 5 people who on my podcast who are like science communicators, and each of them had their own perspective, and everything I think, like, in the grand scheme of things, kind of makes a lot of sense. Like, you spoke about how we are publicly fund, like scientists, or like the science research or whatever is happening is all like publicly funded because of tax money, and it's our responsibility to tell them how we're putting the tax money to use, which is a very good point. And so, like, from each of these speakers have given me interesting perspectives, and I really enjoy listening to that. So, what are your projects? If you can tell me about how you practice your communication, how do you communicate your science with the general
so
public, or
yeah, so 2 years ago, I and a friend, so her name is Rupkata from Indian Institute of Chemical Biology. So we
hmm.
started what is called the No Nonsense Science Club. So my
Hmm.
way of science communication is to debunk myths and misinformation as science.
Right,
So it's not just about talking about science that is actively going on, but also about what is the science behind so many myths which are there. I mean, not the science behind so many myths. It's about debunking the myths and misinformation, because you will see that, especially in COVID times, especially you
right,
will see that there are a lot of WhatsApp messages, and social media is just so prominent that anything that comes on social media gets forwarded. Like, people don't even take time to read forwards or reflect upon it before forwarding it to others.
right,
Like, you get one message, it just gets forwarded to the other person. So there is a culmination of misinformation in the community. So one has to break that. And I think that's something that I took upon myself. And India is diverse in terms of language. So what we do is we take different concepts. For example, there was this claim that coronavirus is a bioweapon and it is not exactly a
Hmm.
virus, right? A
It
natural
is
thing.
it is a conspiracy theory. Yes, a
It
well-known
was a
conspiracy.
conspiracy theory. So we
Yep.
took that, we debunked that, saying why it is not a bioweapon. We gave facts about it. And what we do is we also have a couple of volunteers who translate the content into 10 different regional languages, 10 different Indian languages. That
Right.
is something
That's interesting.
new. We also conduct clubhouse session. Clubhouse is the recent
Hmm.
sensation,
Right.
and we also carry out small discussion sessions on clubhouse as to on different topics like climate change, because then you have climate change deniers, and then
Oh
you
yeah.
have
Yeah.
anti-vaxxers and all that. So this is something that I work on actively. Apart from that, I also write science for a couple of magazine, and then
Okay.
I was part of the Optical Society of America student chapter when I was
Mm.
in ICER Thiruvananthapuram, where I go and teach science optics based classes for school kids and college students as well sometimes. So
Hmm.
that's about it.
That's really interesting. And there's no nonsense science club. Is it on a particular platform? Is it
It is
in person?
mostly the we write articles. It is on no nonsense science .in, no nonsense science club.in. You can check it out,
Okay,
and
I'll link it in the
it's also
profile.
there on, yeah, it's also there on Instagram, Facebook.
Okay.
In Facebook, we are still not very active, but we firmly believe in following the footsteps of several rationalists like Narendra Dabholkar, Gauri Lankesh, and Kalburgi, who lost their lives, because of being so active science communicators and
Hmm.
rationalists. More than science communicators, we have to be rationalists. That's what
Yeah.
I believe in. Believe in evidence. Just because there is no evidence doesn't mean you just believe in whatever comes your way. Have your intuition. Believe in what people say. Uh, not
Yeah.
what
The
people
lack.
say. It. Yeah, think a lot. That's very very important, especially in this age where there is a rampant amount of misinformation and myths.
Right.
So, for example, even very important topics like menstruation and all that, a lot of taboo surrounding that. And even talking about taboo, it all comes because of all these stigma and everything is because of a lot of myths and
Hmm.
misinformation. Saying you're not supposed to touch the plant will die
Right. Yeah.
if you're menstruating. So right. So that's our next project, to work on a series of posts based on
Hmm.
myths, misinformation surrounding menstruation.
That's
So we are
interesting.
working on that.
Wow.
Yeah.
That's amazing, and more power to you and your team. Um, well, I think that's it for today. I really hope you can come back some other time where we'll probably talk about other superheroes or like other science fiction concepts that people are interested. Well, thank you very much for giving me your time and explaining in detail about these things. It was really fun, and I hope our the subscribers and our viewers also understand the science behind these concepts and not just take this at face value because we're all we don't claim to be experts. We are just telling you this is what it is. So that is exactly what science is. We're not claiming that we know everything. We're just saying this is what research shows, or this is what this is the evidence so far. So please go back and do your research and figure out new things. And if you have an alternative theory, or if you have another theory to explain some of the concepts that we've just discussed, you can post it in our comments, and we would definitely be happy to go through that. So yeah, thank you very much, Shiva, for coming here and talking to us about all these interesting topics. I will link your Twitter handle and your no nonsense page with the profile. So if anyone who's interested can go and reach out to you or read about your other initiatives.
Yeah, thank you so much for having me today at the podcast series. And I wish more and more podcasts come your way, and I'm really looking forward to it. And thank you again for having me. It was such a fun session, and
Yeah.
I had a great time discussing some concepts about superhero and everything. It's been a while since I talked about superheroes.
Yes.
A lot of fiction, but good amount of facts as well. I think why we need to talk about superheroes is that it's an easy way to engage kids in science.
Right.
So, talk about superheroes, but also give them the facts about it, and then
Right.
it would be a fun place for them to explore more and more because that's where kids are interested in,
Right.
right? And still, there is a lot more to discuss. We mostly
Hmm.
discussed on superheroes who have powers related to light and everything.
Right.
So maybe some other time we can discuss about the speed, the time travel thingy, which I'll have to
Yeah. Oh
talk
yeah,
about.
sure, sure. Yeah, I
Yeah,
think that's gonna be a topic, a different
yeah,
topic
that's
altogether.
that's a huge one. So thank you so much for having me. It was a pleasure talking to you.
Likewise, yeah. So I hope our subscribers and our viewers had a great time listening to this episode. So please like, share, and subscribe, and yeah, just be stay curious, be passionate, and nothing is rocket science. So see you in
Yeah,
another episode. Bye.
thank you. Bye.